Hello, namaskar and welcome friends. Chi-square test of goodness of fit, and now we are going to take a few cases on binomial distribution, Poisson distribution, etc. Now first we are going for binomial distribution, and the case is: a professor in statistics assigns a task of testing whether the four dice or other four given cubical dice are unbiased or not. The professor seems to be a creative person, and through experiments he wants to teach statistics, and hence he gives four dice to a small group of students and assigns a task of testing whether the dice are unbiased or not. The students tossed the four dice 112 times under the homogeneous condition and recorded the results of obtaining odd numbers on various dice. On a cubical die there are 6 sides, 1, 2, 3, 4, 5, 6, and out of them 3 are odd numbers, 1, 3 and 5, and 3 are even numbers, 2, 4 and 6. So they preferred to get odd number as success, and they recorded. Before going further for testing, one of the students observed that the experiment satisfies all the conditions of binomial distribution and told this fact to his professor. Yeah, the student is somewhat, say, maybe cleverer than the other, or his observation is more powerful than the other student. So he observed that all the four conditions of binomial distribution this experiment satisfies. One is number of dice limited up to 4. 2 possible outcomes: success, getting odd number; failure, not getting odd number, P and Q. All the 112 results are, or rather all the tosses, 112 tosses, and their results are independent of each other. So these are the conditions, and the experiment satisfies all the conditions of binomial distribution. That means we can use binomial probability to go further. And also fact to the professor, and the professor also assigned an added task. We are always habituated to do so, of testing whether the experiment follow binomial distribution or not. Yes. The professor also told them that also test whether the experiment follow binomial distribution or not. That means actually we are now dealing with two types of hypotheses. One is the four dice are unbiased, and another is the experiment follow binomial distribution. How to cope up? This is a unique case. Two hypotheses, rather two different kinds of hypotheses are to be tested through a single case. In this particular case, this is possible, because to test the, say, biasness or unbiasedness of the four dice, we need to find out the expected frequency, because we should go for chi-square test, and for chi-square test we should have expected frequencies. So if we use the binomial distribution to calculate the expected frequencies, of course through the available data of this particular experiment, then we can simultaneously test both the things, whether the dice are unbiased and whether the experiment follow binomial distribution or not. Okay, let's go further. If the experiment follows binomial distribution, then what is the situation? Small n. We all know the formula of calculating probability of, say, happening something with the help of binomial distribution, and n is number of dice here, that is 4, finite and fixed. Probability of success, P, is probability of getting odd number, because they have recorded the results of getting odd numbers on number of dice. Yes, so it is 1 by 2, because there are total 6 sides, and out of which 3 represent odd numbers. So it is 3 by 6 or 1 by 2. Q, probability of not getting odd number, that is 1 minus P, that is 1 by 2. And R or X, whatever you take, they are 0 to n, that means 0, 1, 2, 3, 4. Now, first of all, let's add the results. 112 results obtained are number of dice showing odd number on top and number of times that happens. 0, that means no odd number on any of the 4 dice, that happened 10 times. Odd number on only 1 dice, that happened 25 times. Odd number on 2 dice, any 2 dice, that happened 40 times. Odd numbers on any 3 dice, that happened 30 times. And odd number on all 4 dice, that happened 7 times. Now, first of all, if we want to use binomial distribution, what should we do? First of all, what is the formula of binomial probability? Formula of exactly R success is equals to NCR into P raised to R into Q raised to N minus R. That is our formula. Let's substitute all values except R in this case. So probability of R success is in this case will be 4CR into half raised to R into half raised to N minus R. Okay? And if we want to find, okay, let's simplify first of all it. That will be 4CR into half raised to R into half raised to N minus R. So it will be summation of powers and ultimately it will be half raised to N. That is 4CR into half raised to 4. That is 4CR into, half raised to 4 means it will be 1 by 16. Now our aim is to find out the expected frequencies on the basis of the binomial distribution formula so that we can test both the hypotheses. Expected frequency equals to capital N, that is total number of times the experiment was performed, into probability. And here N is 112 and probability is 4CR into 1 by 16. That means it is 112 divided by 16. Yes, 112 is 16 into 7. So ultimately the formula to calculate expected frequency is with us 7 into 4CR. If we substitute various values of R 0, 1, 2, 3 and 4 in this derived result, we can have the expected frequency. So we are calculating the expected frequencies with the help of binomial distribution because the particular experiment follows binomial distribution. So let's calculate expected frequency. 7 into 4CR. If we take R as 0, 4CR will be 1 and 7 into 1 will be 7. So it will be 7. 7 into 4C0 is 7 into 1, that is 7. Okay, next will be 7 into 4C1. That means 7 into 4. So it will be, 28. 28. Third will be 7 into 4C2. That is 7 into 6. It will be 42. Next will be 7 into 4C3. 4C3 means equivalent to 4C1. 7 into 4. 28. And 7 into 4C4. 4C4 is always equivalent to 4C0. 7 into 1, 7. 7. And it will come to 112. So now we have all the expected frequencies. So now we can go for O minus E. 10 minus 7, 3. 25 minus 28 minus 3. 40 minus 42 minus 2. 30 minus 28, 2. 7 minus 7, 0. O minus E the whole square. 9, 9, 4, 4, 0. And to calculate chi-square, we should go for O minus E the whole square divided by E. 9 divided by 7. 9 divided by 7 will be 1.286. Then 9 divided by 28 and the result will be 0.321. 4 divided by 42, the result will be 0.095. 4 divided by 28, 0.143. And 0 divided by 7, anything will be 0 and summation comes to 1.845. And this summation of the column O minus E the whole square divided by E is the chi-square. So with the help of binomial distribution we can easily calculate the expected frequencies, but it is compulsory or obligatory that the experiment must follow all the conditions of binomial distribution. Here the experiment follows the conditions of binomial distribution. That's why we can use the binomial distribution to find out the expected frequencies or to find out the probabilities to calculate the expected frequencies. This is nothing, this is shortcut. Otherwise we can have the long route also. We have to calculate probabilities of all these 5 possible results through this formula and then multiply that probability with n, that is 112, capital N. And then the same expected frequency can be there. This is nothing but the official shortcut. You can always use this kind of shortcut because it is actually not shortcuts, that is use of our understanding. Now let's take null hypothesis. And the null hypothesis is the 4 dice are unbiased. And since we have calculated probabilities, or since the experiment follows binomial distribution, or rather satisfies all the conditions of binomial distributions, we also take the hypothesis as the experiment or the data of the experiment follow the binomial distribution. Alternative hypothesis will be the 4 dice are not unbiased, or we can say that are biased. Actually, it is not necessary that all 4 are biased or not. Any one of 4. Barabar? At least one rather. And because of this, it becomes one tail test. At least one die is not unbiased. Okay? Similarly, the experiment or the data of the experiment don't follow, I use don't because of the word data, follow the binomial distribution. Yes? Okay, let's write this into brackets. And now we have been given that level of significance is 5%, alpha 0.05. Since the chi-square test of goodness of fit is one tail test, and also we can see that this is one tail test, because we cannot conclude everything for all the 4 dice. Biasness is actually possible in case of only 1 or 2 or 3 or all 4. So the alternative hypothesis, the correct way to write the alternative hypothesis is at least one die is not unbiased, or at least one die is biased. That is the most proper way of writing or considering the alternative hypothesis in this case and this kind of all cases. Okay, on the basis of the data we can say that degrees of freedom is k minus 1. Here k is 5. 1, 2, 3, 4, 5. Yes, in case of binomial distribution, never, first of all let me clarify that why am I using sign k? Because in many or most of the reference books, the authors prefer to write the sign n in case of expressing the, say, or showing the calculation of degrees of freedom, but I am using k. Why? Because if we use n, it creates confusion whenever we want to test the goodness of fit of a data with respect to binomial distribution. In case of binomial distribution, this maximum amount of possible outcomes becomes n for this formula. And if we use n also here, then it will create confusion. It is possible we take 4 here. We should not take 4 here. We are not taking the highest value. We are taking the number of class. All possible outcomes of the experiment. So, k is not 4 in this case, k is 5 in this case. Whenever you perform the chi-square test of goodness of fit for binomial or Poisson distribution, always take care wherever you write or whenever you write the degrees of freedom. Okay, it is 4. And critical value of chi-square for 4 degrees of freedom at 5% level of significance is, okay, yeah, one more thing. Since this is binomial distribution and we all know that we can not calculate the probabilities until we come to know the probability of success. Yes. So, calculation of probability of success is necessary to go forward to calculate the binomial probabilities. We have to subtract 1 for calculating P. Now, this is somewhat a matter of arguments and difference of opinions. Some authors don't prefer to subtract additional 1 for calculating P. And there are some or many authors who suggest subtracting 1 additional for calculating P. I am one of them. Yes. Similarly, in case of Poisson distribution, we have to subtract additional 1 for calculating mean or lambda. Yes, that we will discuss at the time of studying Poisson distribution with respect to chi-square test. Now, critical value of chi-square for 3 degrees of freedom at 5% level of significance comes to, from chart it is 7.815. Now let's compare. Chi-square calculated is just 1.845. Chi-square critical 7.815. That means calculated value of chi-square is less than the critical value. Hence the null hypothesis is accepted. So we can conclude that the 4 dice are unbiased and the experiment follows the binomial distribution, or the data follow the binomial distribution. Yes. How can we also arrive at the conclusion that the data or the experiment follow binomial distribution? Because we use the binomial distribution for calculation of expected frequencies. So both the hypotheses, we test both the hypotheses simultaneously. Not in all cases this is possible. In this case, the experiment follows the conditions of binomial distribution. That's why it was possible to test both the kinds of hypotheses. Yes, I hope this unique case will be useful to you to understand the concept of fitting the binomial distribution as well as chi-square test of goodness of fit, whether the data or the experiment follow binomial distribution. forget to like this video, or rather this lecture, this video. Also suggest these to your friends and classmates and other people. And if still you have not subscribed to my channel, please subscribe. PRASHANTPURR is the title of my YouTube channel. That's it. Thank you very much.